Okay, this video will show you how to do the steady state CFD solution to flow around the cylinder. Now, in reality, the flow around the cylinder is not steady state, as discussed in class. Vortices can be shed from opposing sides, in which case it's not steady state, but we can try to get an approximate drag coefficient out of it by treating it as steady state. So we'll do a steady solution, non-transient. So first thing is we'll draw our tunnel. Okay, and here it is. Here's the tunnel. And you can see, and here you have a scale down here, so you can tell more or less how long it is. And now we're going to put in the sphere, or cylinder rather. Now it's better to put it up close to the entry, and then that's going to be the entry on the left, and leave plenty of room behind for the flow to develop. Now let's reposition that a little bit. So I'm just going to move it. I highlighted it and press transform. We're going to move it, and let's say and the x distance of I don't know. Let's say in the z direction we're going to move it. So we're going to move it 0.2 maybe. Let's preview it. Oh, wrong way. Negative 0.2. Preview. Okay, that looks a little bit better, and apply. Okay, so there it is. So we have our object, which is going to be in the flow. Now we're going to mesh it. All right, so you can see you see all these marks on the cylinder. The mesh is going to go on those, and let's run it. And the mesh will probably come out rather coarse, as you can tell. So we're going to refine it a little bit. So let's destroy the mesh, erase it. And we're just going to then highlight this, the cylinder, and we're going to say the target number of nodes, target node spacing is 0.04 now, so let's cut that in half to about 0.02. Let's make it even smaller. What the heck? Let's apply. And now we're going to have, we're going to hit compute, so we should have a pretty, and just ignore all these warnings and agree to everything it tells you. And there it is. Now we've got a pretty fine mesh around the cylinder where we need it, and need it the most. So now we have our mesh, so it looks like about 2,600 cells. And then we're going to do the physics now. This is going to be steady state. No need to touch it. It's air. You've got all the properties of the air that you need down here. Let's make the flow laminar, because that's what we were going to be doing, because we want to be able to compare to the transient analysis. All right, so now let's tell the boundary conditions. So we click on this first wall, new region, and we're going to make that an inlet. Okay, inlet velocity, and let's say that's 2 meters per second, and we're going to apply. Now you're going to be calculating this inlet speed because you will be assigned the Reynolds number, and based on the diameter of your cylinder and the properties of the air, you calculate what velocity to put into this. All right, so next let's do the exit boundary here. So I clicked on that one, new region. That's going to be an outlet. And again, choose conservative. That means that whatever flows in flows out. Okay, so we got that. Now we just have to, let's define our cylinder here, new region. So that'll be the cylinder. Let's give it a name just so we can find it easier later. Cylinder, and that's going to be a wall also. Apply. Okay, and now we just have to specify these walls here. This one, hold down the shift key, you got both together, and new region, and these will be also a wall, but we want we don't want any friction on that wall, so that the wall interferes less with our flow, so there won't be any boundary layer on that. So you just call that a symmetry type and apply, and then now there won't be any shear stress on that, any friction on that. Okay, so now we got our boundary conditions. Calculation parameters now. Let's raise the number of maximum iterations to 1,000, just because 350 may not be enough. And pretty sure that's all that we have to do for this steady simulation. So we go to, so that was the pre-processing. Now we're going to do the processing. We're going to hit solve to make it go, and you see the residuals are dropping, and they very quickly, and before 100 iterations are done, it dropped to below 5 times 10 to the minus 6 for the residual, which that's how it knows when to stop. So hit OK. Now we want to do post-processing, which is visualizing our presentation. And so let's say we want to see the velocity, contours. You can shade it. Let's show the scale so we can tell what it is. We can put, let's leave the lines out and apply. And there it is. We have, you can zoom in and look at it. And you can see the fastest flow, moving flow is going in the top and bottom of the cylinder, which is what we expect. We expect the flow to accelerate. It's coming in at 2 meters per second, and it's accelerating to almost twice the incoming speed because flow has to get around the obstruction. So that was that. You can also do vectors, right? So usually it's helpful to get rid of these, contours, to look at the vectors. Vectors, let's show them. And you can control the size of them, but there it is. Now you can zoom in and see that. Now you notice you get a nice uniform, you can see the separation here, right? You can see the flow going back, but it's not what really happens usually. In reality, you'll get the alternating, the vortices are going to be shed alternating from the top and the bottom. It's an unsteady situation. There's no final flow field like this one. But we can get a drag coefficient out of it by going to Analysis, hitting the Analysis tab, and clicking on the cylinder itself. And here it tells you first of all, you've got the area, the area of the dimension is 0.888 square meters, which you're going to need to calculate the drag coefficient. And now here you've got the total drag force is 0.299 in the x, those are newtons, and in the z up and down is 0.03. So again, you've got the pressure components due to the pressure differences between the front and the aft end of the cylinder, and the viscous component is due to just the shearing of the fluid along the surface. So there it is. That's how you get the drag force, so you can calculate your drag coefficient. So in the next video, we'll show how to do the transient analysis, which will give a more realistic result, but hopefully it's going to give us about the same drag coefficient. Okay, I'm going to stop it here and move on to the next video.